Alrighty, I think this will be the last video slash lecture for chapter 2, which is kind of cool. So what are we, partway into week 2 right now? So that's going to give me a little bit of time to get some stuff done in chapters 3 and 4 before you guys are there, which is cool. Hopefully I can get ahead of you guys and we can have everything really nice and smooth. All right, so again, we're going to kind of wrap up on chapter 2 here, but this is kind of going to be in the spirit of the last couple videos I made, where I'm really going to once again re-hit some of what is discussed at the end of chapter 2, specifically about hypothesis testing and that section. Again, the scientific method is critical to everything you do, so I just really want to make sure some of these principles that you run into in the textbook, that you've got a really good grasp on them, and then when we go into chapter 3 and start talking about the brain and everything, you will be a researcher, or at least you will have a really good sense of the research process, right from idea, coming up with a question or an issue, to maybe using things like correlations to see if you're on the right track, if the things that should be associated seem to be associated, onward to experiments to actually try to nail down the causal links if it can be. And of course, once you do an experiment, you want to draw a conclusion. So remember, every experiment was kind of set up as you derive a prediction from a hypothesis and you test that prediction. Well, you drive a hypothesis from a theory. Let's be more clear on how we're saying this. And then you test that hypothesis directly. Well, testing the hypothesis means, you created two groups, usually that you expect to be different in some way. And so by the time you've collected your data, you're always left with the question, did I see anything? Is there anything interesting in my data? Specifically, usually, if we go to that control and experimental group kind of approach, do we actually see a difference between the control and the experimental group? Well, how do you know if there's a difference? It's just a bunch of numbers. What makes a given average, let's say, a given mean, different from another one? That's what we're going to talk about a little bit today. Okay, so there will be sections, by the way, on descriptive statistics as well. I'm talking more about what's called inferential statistics in this section. Descriptive statistics are more about representing things and using means and medians and measures of variability, etc. So you should, make sure you have a good feel of all that. But you can use stats to describe your data set, and you can also use it to answer questions. And that's the part we're going to focus on in this video. Okay, so this comes from me having taught the history of psych course now here at UTSC, and suddenly I see everything through a little bit of a history lens. And so I like to kind of give you guys that lens too. And this group of people, the Vienna Circle, are the people whose fault it is that you have to learn all this stuff, quite literally. And look at when they were, 1924, 1936, not that long ago, so about 100 years ago. And psychology itself had been going on for about 50 plus years at this time. And basically, a lot of these scientists, and these are not all psychologists, by the way, it says here philosophers, scientists more generally, but they were watching a lot of different people do a lot of different things and call it science. And, even in psychology, we can go back to Wundt using introspection, focusing on this process of having people look inside their minds and such. And they wanted to formalize a lot of this stuff. They wanted to say, hey, listen, there's so many different things people are doing. It's hard to compare and think about all this. Could we come up with a formal approach to research and to data analysis? Okay, so we've talked about the experimental approach and how that kind of led from this Vienna Circle. And now we're going to talk about the sort of next step in that experimental approach, making decisions based on the data you received. By the way, this whole approach is sometimes called logical positivism. I'm not exactly sure why it's logical or positivism. It's certainly logical. There's a real deep logic involved. Your guess is as good as mine for positivism. We'll have to look that up. Okay, so one of the characters, and the character especially relevant to our statistical side of things, was named Fisher, Ron Fisher. And you just see a little sketch of him here. And I want to talk through some of the Fisher stuff because you're going to come into contact with math, and specifically you're going to come into contact with probabilities. And a lot of students don't like either. They don't like math. They don't like probabilities. They find them kind of hard on the head. But they're not really when you kind of keep them connected to real world events. And Fisher knew this originally, and so when he approached some of his ideas about how we could formalize data analysis, he was very careful to keep it connected to the real world. And in fact, one of the examples he likes to talk about is this woman from England who was making this claim. She was claiming that she could tell whether milk was added to a teacup before or after the tea was poured, right? So imagine you have a cup of tea. Either you add the milk and then put the tea on top, or you add the tea and put the milk on top. And this woman said when she tasted it, she could tell the difference. Do you believe her? How could you come to believing her? What would have to happen to make you believe her? That was kind of the question Fisher asked. And so he said, well, okay, so let's say we ask her to close her eyes or turn her back, and we create a cup of tea, and we either put the cream in first or second, and we ask her to guess. At that point, she's got a 50% chance of getting it right, by chance, right? So if we assume, well, let's go the other way. If we assume she really can do this, then she should be nailing every one of these, right? She should be able to tell us accurately each time. But on this first cup, so let's say she drinks it, and let's say she says the cream was added first. Is she right or not? Well, we'll know if she's right or not, but we can say, even if she can't tell the difference, she has a 50% chance of being right. Right? She'll pick one of them, and we did one of them. So she could pick one of those two possibilities and be right with a 50% chance. So if she does that and gets it right, should we be impressed? Maybe, but not really. It's a 50-50 shot, okay? But what if we do it twice? What if we do that same thing, pour a second cup of tea, either with or without the cream, we ask her to taste it, and she's right again. Now she's 2 for 2. Each time she had a 50% chance of being right. So that means she's only got a 25% chance of being right twice in a row, right? 50 times 50, you multiply those independent probabilities together. Law of multiplicative probabilities, I know, I'm screaming. But you can think of it this other way. Let's just stop here and make sure you're comfortable, because then I'm going to have to just make you assume. But at this point, there's 4 alternatives that could have happened, right? We could have added cream first to the first one and second to the second one, or first to the first one and first to the second one, or second to the first one and second to the second one, or second to the first one and first to the second one. So there's 4 different things we could have done. And if she nails the thing we did, the one of those 4, then she's got a 25% chance. Okay. Should you be excited by that? If she gets it right twice in a row, it's almost like, flipping a coin, and imagine somebody told you the right answer before they saw it twice in a row. Well, a little bit more impressive. She has a 25% chance of doing that just by luck. But still probably not that impressive. What if she went 3 for 3? What if we did it again? Well, and she was right again. Now she's only got a 12.5% chance of guessing right 3 times in a row. Being lucky and just picking the right one 3 times in a row. We know that that's 12.5. What if we take it to a 4th? That's 6.5. What if we take it to a 5th? That's 3.1% chance of getting that right, of getting 5 out of 5 right, okay? And so the question is, at what point do we say, you know what? I think she really can tell. this doesn't seem like she's just guessing and guessing right every time, because we know the likelihood of her guessing right every time, 5 in a row. It's 3%. And in Fisher's mind, there was an important difference that happened right here between 6 and 3. He said, at some point, we have to accept that she maybe can do this. And he arbitrarily embraced 5%. He said, if the chance of her doing it just by guessing is less than 5%, but she does it 5 for 5, I don't think she's guessing. I'm willing to say this isn't guessing anymore. This is her really being sensitive to the order in which those two things are. So he picked 5%. Now there still is, in this case, a 3% chance that she just guessed right for all 5. So our decision could be wrong. We could say, no, I think she can really tell, and we're wrong. And this is one of the things, and I'll end on this point too. This decision-making process we're going to talk about is fallible. It can lead to incorrect decisions. We can quantify how likely those incorrect decisions are. But remember when I always said, in science, we don't say we've proven anything or even disproven anything, because we're always working with probabilities, and we always know that whatever conclusion we reach, it's probably right, but it could be wrong with a certain probability, like about 5% or less, usually. Exactly. All those things you hear on TV. Oh, the average was between this and this, or it was 42 plus or minus 5 or something. And they're always showing their what we call confidence range, confidence limits. But there's always this sense in science that we're dealing with probabilities. That's what I'd say. And therefore, we're not absolutely right all the time, and we don't think we are. Okay. So let's kind of step back from here and just, this is one part of the core decision-making process. If something happening by chance is less than 5% in science, then we tend to think it didn't happen by chance. That 5% becomes a very powerful number for us. It's a p-value, p of less than 0.05. The probability of this happening by chance alone is less than 5%. And that's when we usually reject the idea it happened by chance. I'm going to say these things over and over again because I want them to sink into your brain a little bit as we go through. Okay, so let's move on from Fisher and kind of describe some of the approaches Fisher took. Now, whenever you teach stats, it starts to feel like math, and people go, "Oh, I can't do this." Students think, "This is not what I'm good at." I would like to convince you that when it comes to hypothesis testing, you already know how to do it. You do it all the time. And you do it actually probably in a way not that different from what I'm going to describe. You just don't think about it that way. You don't so what we're going to do is formalize what you probably do relatively naturally. Well, naturally if you're smart. So let me bring in this example. We all have personal relationships in our lives, and we all occasionally have arguments with people that we love, people that we're close to. A classic argument is the worry that person that we love and that we're close to is actually seeing somebody else. Dum. They're seeing somebody on the side. So let's imagine you're in that situation, and here's this person in front of you you care deeply about, and you think they're seeing somebody else. You're starting to suspect this. What do you do? Well, let me tell you what many of us do that's just very wrong. I'll try to teach you how to argue in this situation. What many of us do that's wrong is one person will say, "I think you're seeing somebody else," and the other person will say, "No, I'm not." And they'll say, "I think you are." "No, I'm not." And then it's like, "Yes, you are." "No, you're not." "Yes, you are." "No, you're not." And it just turns into a very emotional thing, and it gets out of control. Okay? And you just end up very angry with each other and upset and sad and etc. Okay, that's one way you can go. You won't get any very useful information from that approach. Here's what I recommend. If you can keep a cool head, which is very important, because this is going to be a sort of logical approach, logical positivism. It's going to be a logical approach we take. So what we're going to say is, okay, listen. I don't want it. I don't want you to be seeing anybody else. I'm hoping you're not seeing anybody else. So I am going to start like even though this is what I think, I think you're seeing somebody else. That's what I deep down think. But I'm going to start this discussion by saying, you're right. Let me begin by assuming for a moment that you're right, okay? You're not seeing somebody else. I'm just overreacting. That's what I want to be true. That's what we all want to be true. And so I'm going to start by assuming that that is true. So we call this the null hypothesis. Even though we kind of think something else is up, we call this the alternative hypothesis. We start by accepting the null. We start by saying, no, I'm wrong. There really is nothing to see here. And the null, that word null means sort of nothing. It's typically associated with no difference between conditions, nothing going on, a lack of something. Whereas the alternative is usually talking about there is something going on. There is some difference there. And so we often begin by accepting the null. And in fact, in this formal hypothesis testing approach, we always begin by accepting the null. So you can do this explicitly with this person. You can say, listen, cool, excellent. I'm going to assume you're right. But then I just have some questions. Okay, there's just some things that are kind of nagging at me. And so let's just talk about these things. You're out at times when you never were before. There were certain times I'd reach out to you and you were in very predictable places, and now you're not, and I don't know where you are. It's hard to know where you are because when you do that, your cell phone is turned off. So not only are you out, you're unreachable at those times. Okay, well maybe there's a reason for that, right? I've also noticed you're really focused on how you look lately. You're spending more time getting ready before you go out. You're trying to shower more regularly, smell nicer, whatever. And we've been seeing each other now for a couple of years, so it doesn't feel like you're doing this for me. And so that seems kind of odd if this is true, if you're not seeing anybody. And well, we could look at some other evidence. You seem less interested in spending time with me. Your stories about what you're doing in these other times keep changing, and you smell like perfume. You never used to. Okay, so what I'm suggesting here is you can start by saying, maybe I'm wrong, maybe you're not seeing anybody, but now here's a bunch of data. And here's the problem. The likelihood of all of this happening, if you're really not seeing anything, seems very low. We're back to the teacups, right? How likely would it be, by chance, if you're really not seeing anybody, there's really nothing going on, the null is right, how likely is it that all of these things would be happening? If it seems to me extremely unlikely, maybe less than 5% likely, then we might reject the null. We might say, listen, I want to believe you, I want to accept you, but the probability of all this stuff happening, if that's true, is really small. And so these two don't fit together. And therefore, I have to reject this and believe that you are seeing someone else. Pull that on your significant other next time. I've looked at the probability of all these things I've seen, and it seems really low. And that's a very logical, rational way to say, you know what, I think I'm right to not believe you. Now, of course, let's just talk about the potential error here, right? So I said there's less than 5% chance. Maybe there is another explanation. I don't know. Maybe this dude is trying to get his girlfriend a great job at this perfume company. I'm getting out to lunch, but he wants it to be a surprise. Why would he be getting her a job? I don't know. I'm just making stuff up. So maybe he wants it to be a surprise. So when he has to meet with them, that's what he's doing when he's out, and he has to turn the cell phone off because he doesn't want her to be able to see who he's with or what he's doing. And these people are only, they care about how he looks. They want him to be very formal when he comes in, so he worries about looking right. I don't know how this one fits. I don't know why the story keeps because he is lying about it, right? Because it's a surprise for her. And of course he smells like perfume because he's going to a perfume place. All of this to say, maybe there is an explanation. And maybe this is all happening, even though this is true. There is a 5% chance we are wrong when we say, we're going to reject this. And we could be wrong. But this is a very, I think you'll now see, sort of logical, structured approach to evaluating some statement. you're not seeing anybody else, and then ultimately rejecting that statement and saying, well, that kind of leaves this one. Okay. I can do a few examples. The textbook did an example or two as well, and I think with some of this thinking in these worlds, more examples are better to get you kind of on track with what you're reading and understanding. So let me come at the same sort of issue, but from a very different perspective. It's a little bit more of a sad situation, I'm afraid, especially for me. This is an obituary. It's really, there's this notion called tempting fate. I'm definitely tempting fate here by writing this down. Professor Steve Jordan was found dead Thursday morning, September 17th, 2020. Doesn't say 2020, but let's say it. He was murdered sometime the night before. Apparently stabbed repeatedly with a blue pen before being struck on the side of the head by a hard object assumed to be a laptop computer. A suspect was seen leaving this home. The suspect was medium height, approximately 120 to 150 pounds, and was wearing a black hat and gray sweatpants. Police suspect students who were in one of his classes in the past or who are perhaps taking a class with him now. Okay, so let's say this is true, okay? And the police now want to figure out, okay, who did this? And maybe they want to interview you because you are a student in my class. And maybe they want to ask you a few questions. Are you a student? Well, you probably are. Now, some of you guys might be just watching these lectures for fun. Maybe you're not a student in my class right now. But do you have a black hat? Do you have gray sweatpants? Do you weigh between 120 and 150 pounds? I should have put in here too. Are you about medium height? Do you own a blue pen? Do you own a laptop? Do you have an alibi for all of Wednesday evening? That is there any point during Wednesday evening during which you were alone or there's nobody there that can attest to you being, not murdering me, that you were somewhere else? Okay, so I just these were 7 questions. Let me throw that 8th one in there too. Medium height. I wish I had 10. I'll tell you why. But imagine there's 10 things like this. Okay, so we have 7 or 8. How many of them did you say yes to? These are the things they're looking for in a suspect. Every time you say yes to this, you're looking a little more suspicious, aren't you? Quite possibly. This is sort of evidence. So let's kind of take this and say, okay, let's assume there were 10 questions and we actually saw how many people had 0. They said no to all of them versus saying yes to 1, yes to 2. So more people say yes to 2, even more said yes to 3, even more said yes to 4, even more. So mostly said yes to 5. Few less saying to 6, 7, 8, 9, 10, etc. Now, if we did this with all of you guys, and if I only went up to 7, we would see that sort of distribution, that of those 7 that I just described, most of you guys are probably around 4. And then there's some of you around 3 and 5, not as many as 4, but more around 3 and 5. And then there's less of you, but still some that are 2 or 6, and less of you and still some that are 1 and 7, right? So we see this what's called a normal distribution because it's so common. Just about anything we measure has this sort of shape of distribution, which is, by the way, a descriptive way of presenting data. This is the description when the null is true. And what do I mean by that? Here I am. I'm not dead. I'm still alive. Not dead yet. So, in this example we just did, we know that none of you are the murderer because there was no murder. And yet, we still can see that for some of you, there was a lot of evidence that you might have been the murderer had there been a murder. So for every crime that's committed, we could pick an individual, and there would be some amount of evidence to suggest that individual might have done the crime. Even creating a random crime, there is some amount of evidence that you might have done it. We, of course, become interested in these people, right? These are the people that said yes to a lot of the questions. And so that's where we start to say, okay, how likely is it that somebody would have said 9 or 10, or in your case, 6 or 7? Some of you said 6 or 7, right? Some of you had 7 yeses there. I'd love to know how many. I'm going to ask after this, just so we can all see the data, I hope. But some of you will have had 7 bits of yeses. Even though you didn't murder me, there's a lot of evidence to suggest you did, right? And so when we're looking at something like this, we often look at a tail of the distribution like this and we say, well, what's the likelihood of this happening by chance? Of somebody saying yes to every question by chance? Is it less than 5%? And I kind of can tell you that with 7, it's right back down to the teacups, right? Remember, we only got to 5 teacups and it was 3%. So with 7, it would be 1.5. It would be like point. It'd be less than 1% chance of you getting 7 out of 7 in a row. 1 out of 100. Well, you know what? There's 1,600 people in this class. So there's probably about 16 of you that got 7 out of 7 on that. If I had been murdered, you guys would be looking very guilty right now, but you'd be innocent, right? And so this is just to get you into that sense of probabilities, this is how we do things. We try to get a sense of what's the likelihood of certain outcomes happening by chance. And then we say, okay, now what did we actually see? And just about every statistics formula that you will meet in your statistics class will be a measure of the effect you saw over a measure of how much we would have expected by chance. And if you're seeing a lot more evidence than we would expect by chance, so if this numerator is much bigger than the denominator, then we start to suspect this isn't chance. That evidence was not chance. That evidence is there because you did something, because something is going on. And so we reject the null hypothesis and accept the alternate. I don't know if that helps. I hope that helped. Again, just trying to kind of bend your mind around this in a couple of different ways. There's one more way I want you to see, because I thought it was pretty compelling too. And I want to use it, I want to mention it for 2 reasons. One is, as I was thinking, how can I best explain this to the students? How can they get this sort of probability and p-values and what they all mean? Because they're so important to what we do. And so I decided to look on YouTube, look around some videos. Is there anybody there that explains it in a way? And there's lots, okay? And so let me just say in general, if you're having trouble with the scientific method or anything you encountered in this chapter, poke around on YouTube. There are great presentations by highly intelligent people that can expose you to the information in a different way. Now, I've included one. I've included a video below that I found where a woman who works at Google is talking about what p-values mean, and she uses this great dog example. At least I think it's a great dog example, and I love a good concrete example. And I thought in a short period of time, she did a really good job explaining what I just tried to explain to you as well. So check it out, just to make sure you got your p-value stuff straight, but also think of this as a strategy you can use. Anytime you run into something that's challenging, take a look online and you'll find all sorts of good resources there to help you learn these concepts in a deeper way. Okay, I'm going to leave it there. That's going to be it for chapter 2 for me. I will see you in chapter 3 when we start talking about the brain. It'll get fun from here. Let's do it. Bye-bye.